So in the last video, we talked a little bit about Lyapunov exponents as well as their generalization to systems of first-order equations. But now we haven't really talked about stability at all in first-order systems, although we did talk about it sort of in general when we first introduced the notion of stability. In this lecture, we're going to talk a lot more about actually formalizing the generalization of ideas like stability to first-order systems of difference equations. So, to begin, let's recall what we mean by locally asymptotically stable. So recall that x sub t plus 1 is equal to f of x sub t is stable. Actually, let me go ahead and say locally asymptotically stable. Asymptotically stable, which we've been sort of using interchangeably for a number of these systems. Because when things aren't discontinuous, you often there's a correspondence between the two. But let's be a little bit more precise right now. So a system is locally asymptotically stable at an equilibrium x bar if the first derivative has magnitude less than 1 at x bar. And it's unstable at an equilibrium x bar if the magnitude of the first derivative is greater than 1. So what's the equivalent for first order systems? So what is the equivalent for first order systems? Well, at the very end of the last video, we talked a little bit about how you can use the Jacobian to compute the Lyapunov exponents. It turns out that the Jacobian is actually the correct generalization of the first derivative, as you should recall from your multivariable calculus class. So let's go ahead and state a fairly general theorem. This is not numbered in your textbook, since your textbook separates out second-order systems and nth-order systems in a sort of weird way, and I'm just going to lump it all together, and then we can go back and give some of the specifics for n equals 2 or n equals 3. So let's suppose we have a system, let x of t plus 1 be equal to f of x of t, where these are all vector valued, be a system of n first order equations. So on x of t, where x of t is equal to x1 of t through xn of t transposed, and our function f is a set of functions f1 through fn also transposed, and we have that fi is a function fi of each of our individual scalar variables x1 through xn. Okay, so the usual setup for a system of first order equations, except that we're now working with a nonlinear system. So f is no longer just a single matrix, it's a nonlinear function. Okay, and let x bar be an equilibrium of the system. Be an equilibrium of the system. When the linearization of the system about x bar and letting u of t is equal to x of t minus x bar. So we're going to shift everything over. So that gives a system. U of t plus 1 is equal to this matrix J times u of t. J times u of t, where J is the Jacobian matrix of f at x bar. And so we can also write the Jacobian as a function of x bar, since it is dependent on it. So j of x bar is going to be equal to the partial derivative of our first function with respect to x, the first coordinate at x bar, let me write that a little bit more clearly. At x bar, df, the derivative of the first function at the second coordinate, along the second coordinate of x bar, and so on, all the way through the df1 dxn of x bar, and so on. And of course, we go the other way. So this is dfn dx1 of x bar, and this here is dfn dxn of x bar. Okay, so this is the standard definition of a Jacobian. So given that and that is the correct higher dimensional analog of the derivative. Okay, well then what we have is that x bar is locally asymptotically stable. If all the eigenvalues have magnitude less than 1. So for all eigenvalues lambda I, and unstable if some lambda I is greater than 1. Okay, so this is in many ways the same sort of idea as in just a first order in just the first order equation where we were just talking about the derivative. Now, instead of talking about the derivative, we're talking about the eigenvalues of the Jacobian, which since you have all these different directions that you could be going, and so we're talking about all the eigenvalues of the Jacobian instead of just a single derivative. Okay, I'm not going to prove this in full, but let's go ahead and give a sketch of the proof. And so this is going to be very similar to our proof of the in the other case. So in the one-dimensional case. So for x naught, such that x bar minus x naught, this distance is less than epsilon, with epsilon sufficiently small. We can approximate. X of t plus 1. Actually, let me call it x of 0, just so my notation remains the same. It's obvious, so the notation doesn't make that much of a difference, but let's try to avoid confusion there. Well, this is equal to, can approximate this by using the Taylor series. By the Taylor series, series of f, keeping only the linear term. So we have x of t plus 1 is approximately equal to f of x bar plus the Jacobian at x bar times x bar minus, x of t minus x bar plus 1/2 times the x of t minus x bar transpose times the Hessian matrix of x bar times x of t minus x bar, and so on. So you have all these other higher order terms, where this here is the Jacobian, and this here is the Hessian matrix, and so on. But now we can approximate it by just getting rid of all these other terms. So we're just going to drop those off, and so long as you're close enough to your point and you have continuous derivatives, this approximation holds in the small neighborhood around your equilibrium. Okay, but when we write it out this way, this implies that x of t plus 1 minus x bar, since f of x bar is just equal to x bar, so let's move it to the other side, minus x bar, that's equal to j of x bar times x of t minus x bar for x of t sufficiently close to x bar. So if we were being super careful, you could write a delta epsilon proof, or you could like actually bound the error in terms of some epsilon. We're not going to do that right now, but that is something you can do if you want to make this proof formal, which it is not right now. But if we rewrite that, we get u of t plus 1 is equal to j of x bar times u of t, which then implies that u of t plus 1, actually I should approximate. So then u of t is just repeated multiplication by this matrix, j of x bar to the t times applied to u of 0. So now, if all eigenvalues lambda I are less than 1, if all the modulus of all the eigenvalues are less than 1, then the spectral radius of j of x bar is also less than 1. And we know from chapter 1 that if the spectral radius of j of x bar is less than 1, then the limit as t goes to infinity of j of x bar to the t goes to 0. So the limit as t goes to infinity of x of t is equal to x bar. Okay, and if we have lambda I is greater than 1 for some I, then so long as we have some component in the eigenvector corresponding to x bar, let's see, as long as x of 0 minus x bar, the dot product of that with vi is not equal to 0, where vi is the eigenvector. I is the eigenvector associated with lambda I greater than 1. Then the limit as t goes to infinity of u of t is equal to infinity. Of course, the linearization breaks down. The linearization may break down as the distance from x bar grows, as x of t minus x bar, that distance grows. But x of t will still leave a sufficiently small ball around x bar. So it is not stable. So it's unstable. This is very not rigorous, but it sort of gets at the flavor of the sort of argument, and it's basically the same argument that you're making with the derivative, except you have to be a little bit more careful because you're working with the Jacobian and different eigenvalues and eigenvectors instead. Okay, but once we have this, so basically what we've done is we've just said that figuring out the stability of a first order system of equations is basically entirely determined by whether the eigenvalues are less than 1 or there's some eigenvalue that's greater than 1. And so we can apply this in the lower dimensional cases. So I'm going to give a couple of sets of so-called jury conditions. So these are conditions you can quickly check to see if you have some eigenvalue less than 1, and they'll tell you if a system is stable. So this is a slight modification of theorem 2.10 in your textbook. So if we're going to let's suppose J is a 2 by 2 matrix. Well, then lambda I is less than 1 for all eigenvalues lambda I if and only if the trace of our J matrix is less than 1 plus the determinant of our J matrix, which is less than 2. And almost conversely, though not quite, lambda I is greater than 1 for some eigenvalue lambda I if at least one of the following conditions is true. The following is true. So you need at least one of the trace of J is greater than 1 plus determinant of J, or trace of J is less than minus 1 minus the determinant of J, or you need that the determinant of J is greater than 1. Okay, and the proof of this is a little bit tedious, although it's a little bit tedious, but all you have to do is you basically check that this is equivalent to the eigenvalue condition on a 2x2 matrix. Let me go ahead and I'll do the proof in the next video, since it is a little bit long and gets away from the sort of big picture of this, which is that you want to check the eigenvalues. Instead, let me go ahead and state another jury condition, which is useful when your dimensionality is 3. So theorem 2.11. So these are the jury conditions, or they're sometimes also called the Schur-Kohn criterion, when n is equal to 3. And here, instead of writing out the actual matrix, I'm just going to talk about the characteristic equation of the matrix, since that determines what the eigenvalues are. So you don't have to worry about that so much. So suppose we have some p of lambda. So this is suppose this is some characteristic equation. So it's lambda cubed plus a1 lambda squared plus a2 lambda plus a3, where a1, a2, and a3 are in the real numbers, and that's a polynomial. This is a third-degree polynomial. You can think of it as the characteristic equation of a 3x3 Jacobian matrix, which is what we care about in this particular case. But this theorem doesn't require that this be a characteristic polynomial. It just is any polynomial of order of degree 3. So then the solutions, lambda 1, lambda 2, and lambda 3 of p of lambda is equal to 0. So these would be the eigenvalues of the characteristic equation. Those satisfy lambda I is the absolute value of lambda I is less than 1 if and only if all three of the following conditions hold. So let's see, we have p of 1 is equal to 1 plus a1 plus a2 plus a3 is greater than 0. And condition 2, we have minus 1 cubed p of minus 1 is equal to 1 minus a1 plus a2 minus a3 is also greater than 0. And the last thing we need is that 1 minus a3 squared. So what you have is 1 minus a3 squared has to be greater than the absolute value of a2 minus a3 times a1. Okay, and so these are necessary and sufficient conditions for n is equal to 3. And for the case of general n, where things are a little bit harder because this third condition turns out to be a little bit harder to generalize, but we can give necessary conditions for that case. So if the solutions lambda 1 through lambda n of p of lambda is equal to 0, where we have a degree n polynomial, where p of lambda is equal to lambda to the n plus a1 lambda to the n minus 1 plus dot 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 plus a n minus 1 lambda plus a n. If that satisfies lambda I has magnitude less than 1, well, then you again have three conditions. The first one is the same. P of 1 is equal to 1 plus a1 plus a2 plus dot 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 plus an is greater than 0. Condition 2 is minus 1 to the n p of minus 1 is equal to 1 minus a1 plus a2 minus dot 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 plus minus 1 to the n an. That also has to be greater than 0. And the third condition is going to be slightly different. It's going to be a slightly easier to check condition. That's going to be the absolute value of an is less than 1. So these are necessary but not sufficient. So necessary but not sufficient. Well, this is something that is a check to see if it's not the case, but it's not quite sufficient because the actual condition is a lot more complicated, and the derivations of all these jury conditions are highly non-trivial. In the next video, we'll be deriving it for the case of n equal to 2, and you can see that that already starts getting a bit tricky. And for the cases of n equal 3 or for arbitrary n, the proofs are rather involved. So we won't be going into those in too much depth. But now that we have this, we can also give another very useful definition. This is definition 2.9. So we can define hyperbolic and non-hyperbolic equilibria of systems. So, and the definition will be basically what you expect. So recall that the definition of hyperbolic and non-hyperbolic for a first-order difference equation was just whether or not the absolute value was equal to or not equal to 1. In this case, we'll just be checking if the eigenvalues are equal to or not equal to 1. So let x bar be an equilibrium of our system, x of t plus 1 is equal to f of x of t. And we're going to let J of x bar be the Jacobian matrix. Jacobian matrix at the equilibrium x bar. X bar is hyperbolic. If the absolute value of lambda I is not equal to 1 for all eigenvalues, lambda I of J of x bar, and otherwise it is non-hyperbolic. Note that in our definition, we're only going to call it hyperbolic if all of the eigenvalues are not equal to 1. So if all eigenvalues have magnitude not equal to 1. Because if you have eigenvalues that have magnitude equal to 1, you can sometimes get weird behavior at the equilibrium because of things that are neither going farther away or nor getting closer. But in the case where all the eigenvalues are not equal to 1, well, then the stability conditions that we've checked are fairly straightforward to check because things are either exponentially moving away or moving closer. And otherwise, it's not hyperbolic, and that's a case where you need to do a lot more special case analysis. Okay, thank you very much. And in the next video, we'll go back through and prove the case for n equal to 2, as well as give an example of applying some of these jury conditions and to a model.